Hashing is the silent engine behind modern web, turning the chaos of massive datasets into near instant search results. Good morning, everyone. I am Swayam, and today I will be walking you through the fundamental mechanics and applications of hashing in data structures. At its core, hashing is the most efficient way to achieve speed in data management because it aims for the constant time complexity of O of 1, while other structures like trees or linked lists might require us to traverse through half the data just to find one item. Hashing uses an array-like function called hash function to map data of arbitrary size, like a long string or a complex object, into a fixed value. Think of it as an intelligent GPS for your data. Instead of checking every house on a street to find a specific person, you have a function that takes the name and gives you the exact house number immediately. This transformation of search key into an array index allows for direct access. The very first rule of a reliable hash function is that it must be deterministic. This is the foundation of data retrieval. It means that for a given input, the function must produce the exact same output every single time. This is essential. Imagine if you stored a piece of data today, but when you try to look it up tomorrow, the hash function gave you a different index. The data would be effectively lost in memory. Determinism ensures that the path to your data remains same, and in a technical sense, your hash function should not rely on external factors like current time, random number generators, or memory addresses that might change between program executions. It must be a pure mathematical mapping, same input, same output, without exception. The second essential rule of a hash function is maintaining a fixed length output. This is a fascinating aspect of mathematics involved, regardless of the size of the input data, whether it's a single character, a student ID, or an entire digital book. The result hash value always remains of the same size. This property is critical because it allows us to map unpredictable, arbitrary data into a very specific, predictable range of array indices. By condensing all possible inputs into a uniform format, we create a standardized address system. This ensures that our memory allocation remains efficient and that every piece of data, no matter its original complexity, fits perfectly into the structure designed in our hash table. The third pillar of a robust hash function is that it must be irreversible. In a computer science, we often refer to this as one-way function. This means that while it's computationally simple to turn an input into an hash value, it is mathematically impossible to reverse engineer that hash value back into the original value. This property is what transforms hashing from a simple organization tool into a vital security asset. This is the foundation of data security. Even if an attacker gains an access to a list of hash values, they cannot work backward to discover the sensitive information, like a private password or a specific search key that created them. This ensures that even when data is indexed for speed, its privacy remains intact. Now that we understand the rules, let's look at how function together within the hashing ecosystem. This process follows three distinct steps to bridge the gap between abstract data and physical memory. The search key, the input value to be stored or the retrieved, is the search key, basically the raw input value. Next is the hash function. This is the mathematical engine that takes a search key and using methods like the division or multiplication method transforms it into a small integer known as the hash value. Step 3, the hash table. This is an array consisting of bucket or slots. The data is stored at an exact value provided by the hash value, allowing for that instant access that we discussed earlier. By acting as a bridge, that hash function ensures that every unique key has a dedicated home in concrete memory locations. Now I will look into two different examples. These two examples have two functions. Both of them are deterministic. Why are they deterministic, you may ask? This is because in the first function, we can see that whenever we pass, let's say 10 and 20, we always get 30 as the output. However, if we pass 100 and 200, we'll always get 300 as the output, which is always true. Now, The next information for both, this is where both of them fail. This is because if we pass 10 and 20, we get an output of 30. But if we pass 100 and 200, we get 300 as the output, which is not of the same length as the previous output, which is not a fixed length. And in the increment function, we can see that if we give 10, we get 11. We give 100, we give 101. So both ways, we cannot keep the length fixed. Next, for irreversible output, for the first one, you can see that the output is irreversible. From 30, we cannot ensure that it is only 10 and 20. Let's say we take an example of 3. 3 can be formed with the help of 4 and minus 1, or it can be formed by 2 and 1. Both the additions give you the same result. So it is not possible to find out which is the initial values. So for the first one, irreversible output, this is true. But for the second one, we can easily find out what was the previous number. Let's say we get 11. So the previous number is input can be said it is equal to output minus 1. So we can find out. So these are the cases for functions which are not hash functions. Now moving on to a function which is actually a hash function. You can see that it takes two numbers, finds its sum, and then returns the first digit of it. Let's say we take 1 and 5, we get 6, which is an deterministic as well as fixed length as well as an irreversible type. If we give 10 and 25, we get 35, out of which we only take the fifth value. So what we get is one value, which makes it possible the fixed length part. And for is irreversible part, uh, we only take the last value. So it is always not possible to find which is the initial value. However, you can notice that if it is 10 and 25, and let's say we give 1 and 4, the output comes out as 5 both the times. This leads me to the next topic, which is the collision. Even the most sophisticated hash functions eventually run into the collision challenge. In an ideal scenario, every unique key would map to a unique index. But in practice, a collision occurs when two distinct keys produce the same hash value, mapping them into an identical array indices. It is a common misconception that better math can eliminate this entirely. However, despite perfect hash functions, collision remain mathematically inevitable. When we encounter a collision, the first strategy we can use is separate chaining, which is often referred to as open hashing approach. In this method, the hash table doesn't just store a single data point in each slot. Instead, each bucket contains a linked list that stores all elements that collide at a specific index. This approach has distinct characteristics we should know. Infinite growth. One of its biggest advantages is that the list can expand dynamically. Next is the pointer overhead. There is a trade-off in terms of memory because we are using linked list. We require extra memory for node pointers and the overhead of dynamic memory allocation. It is a robust way to handle the inevitable crowding of the indices, ensuring that every piece of data has a place to live, even if it has to share an index with another key. Next is open addressing, also known as close hashing. In this strategy, all elements are stored directly within the hash table array itself. When a collision occurs, instead of building a list outside the table, we use probing techniques to search for the next available open slot within the existing array. The most straightforward version of this is linear probing. Much similar to linear searching, when an index is already occupied, the system simply checks the very next subsequent position and then one after that, sequentially until an empty slot is found. While this is very simple to implement, it carries a specific risk, which is primary clustering. This is where long, consecutive blocks of occupied slots begin to form, which can significantly slow down the performance as the system has to trudge through these clusters to find an open space. Now, we shift from general data structures to one of the most critical real world uses of this technology, hashing in cybersecurity. In this field, we use cryptographic hashing, employing sophisticated algorithms like SHA-256, which stores data in 64-bit formats every time to produce fixed size, irreversible hash values. This is the backbone of modern security. A vital application of this is password hashing. A secure system never stores your actual plaintext password. Instead, it stores a salted hash value by adding a unique random salt to the password before hashing it. We ensure that even if two users have the same password, their hashes will look completely different. This prevents rainbow table attacks and ensures that even if a database is compromised, the actual passwords remain the same. Finally, to conclude, hashing is an engine uh, behind rapid database indexing, web caching, and secure password storage. While it offers incredible overflow and average case performance, we must always weigh that it's against limitation such as memory overhead and lack of support for range queries. Ultimately, hashing transforms the way we store and protect information through clever mathematical mapping. Uh, Thank you for your attention.